this lecture, we look at area to area mapping. Because each pixel corresponds to a small rectangle on the display, when doing the backward mapping, we cannot just map points to points in the different coordinate systems. We need to map areas to areas. If you look here, this pixel is basically a rectangular shape. When mapped onto the 3D object, it warps and the shape changes. And when further mapped to the texture, it gets another shape. Hence, it is better to perform area to area mapping rather than points to points mapping. Another drawback of point to point mapping is that it can cause aliasing for simple flat surfaces. So what is aliasing? Here we have an example. Let's say we want to map this onto a surface, and after mapping it looks like this. The edges are distorted. We sort of get this pixelated kind of object rather than a smooth shape like this. In computer graphics, this refers to the process by which smooth curves or lines become jagged because of the resolution of the graphics device or insufficient data to represent the curves. Aliasing occurs in texture mapping too, and especially if we perform point-to-point mapping. Suppose that we have a periodic looking texture and we map points to points. Then even for flat surfaces, we can still encounter the aliasing problem, especially when the camera zooms out of the scene. This results in each pixel covering a large region of the 3D surface. If you look at here in this example, if we zoom out sufficiently, all these points might correspond to white regions on the texture. And hence, we will only see a white color on the surface of the object, missing out on these blue lines. Mapping areas to areas means that we assign the average shading value of the texture region to the pixel. This helps to reduce the aliasing effect. However, we would still miss the blue strips when the resolution of both the frame buffer and the texture map drops. Now that we have established that area to area mapping is better than point to point mapping, let's look at the mapping part itself. We mentioned earlier that backward mapping functions are difficult to find in general. One solution is to use a two-part mapping. In the first part mapping, we look for intermediate objects that are close to the 3D object on which we want to map the texture. So we want to find an intermediate object which resembles in shape to the final 3D object on which we want to map the texture. And we map the texture first onto this intermediate object. Right? So we map the texture here. In the second part mapping, we map the texture from the intermediate object to the actual object itself. So we go in two steps. From the texture, we go to an intermediate object, and then from there, we go to the actual object. This second part is performed in three different ways that we will see in later parts. Let's look at some examples of two-part mapping. Some common objects on which we can map the texture are cylinders, spheres, and boxes. Here we have a cylindrical shape on which we mapped this texture as an intermediate first step. This slide shows an implementation of the first part mapping. So we have a parametric equation of a cylinder with radius r and height h. The x, y, z can be written in terms of the uv parameters as follows. X is equal to r cos 2 pi u, y is also a function of u, r sine 2 pi u, and z is a function of v only. So given a 3D point x, y, z on the cylinder, we do the following. Find out the parameters uv, and since uv vary from 0 to 1, we can simply let s and t equal to u and v, and s and t are the texture parameters, the dimensions of the image. So we can retrieve the color coordinates s and t from a texture map easily using these formulas by replacing u and v over here with s and t. Note that the range for x and y are from -r to r, and for z are from 0 to h. Here is an example of using cylinder as an intermediate object for mapping texture on a three-dimensional head. Notice that the mapping on the intermediate cylinder is only implicit and it's not explicitly performed. We simply use the UV parametric form of the cylinder to tap into texture coordinates from this texture image, which looks like a cylindrical image unwrapped into a flat surface. We can also use a sphere as an intermediate object for mapping textures. The parametric equations of a sphere are given here. We have x is equal to r cos 2 pi u, y is equal to r sine 2 pi u multiplied by cos 2 pi v, and z is equal to r sine 2 pi u sine 2 pi v. In a similar manner to the cylinder, given x, y, z, we compute u and v. And if we let s is equal to u and t is equal to v, we have a mapping from the x, y, z coordinates of the object to the s and t coordinates of the image. Obviously, there will be some distortions and we have to decide where to put the distortions. Spheres are used in environment mapping. We can also use a box for as an intermediate object for texture mapping. So this is an unwrapped box. This is the top face, the back face, the left, right, and the top face. This is the front face. This is easy to use because it has simple orthographic projections, and they're used as intermediate objects in environment mapping. The second part of texture mapping is to map the texture from the intermediate object to the actual object. There are three ways to map the texture from an intermediate object to the actual object. Normals from the intermediate to the actual, normals from the actual to the intermediate, and vectors from the center of the intermediate object. So this is the first case. Here we have the actual object, which is of course not a perfect cylinder, but we have modeled it with a cylindrical shape, and we are drawing normals from the cylinder to the object. Normals from the intermediate object to the actual object. I have a normal here as well. The second method is normals from the actual object to the intermediate object. So this is the normal vector on this point of the object. This is the normal vector on this point of the object. This is the normal vector on this point of the object. This point of the object will have a normal like this. Notice that different points will map to different locations on the 3D object using these two methods, and it is up to us to decide which one we want to use. The third method is drawing vectors from the center of the intermediate object. This is the center of the cylinder, and going all the way radially outwards. Now we cross this point on the 3D object and we then hit this point on the intermediate object. So hence the texture of this point will be assigned to this point on the actual object, and a texture from here would be assigned to this point. Texture from here would be assigned to this point.